Welcome, my dear beloved students, my dear sons and daughters. Welcome to your favorite YouTube channel, Shashwati Shama. Dear sons and daughters, this is an educational channel guiding the budding degree and diploma engineers in their pursuits of technical knowledge. In the last video, I discussed with you the accessories of a boiler, and there I promised that I would in the next video discuss some aspects of high pressure boilers. Now, my dear sons and daughters, today our discussion will be confined within the aspects of high pressure boilers and to some extent some aspects of thermodynamics. Now, before I start the discussion, I like to define a high pressure boiler. You may ask me question, what is a high pressure boiler? If the drum pressure, that is the steam pressure in the drum of a boiler, is less or equal to 15 kg per square centimeter, then it is called low pressure boiler. If the steam pressure in the boiler drum is less or equal to 80 kg per square centimeter, then it is called the medium pressure boiler. And if the pressure of steam in drum is more than 80 kg per square centimeter, suppose in a boiler the pressure of steam is around 150 kg per square centimeter, then the boiler is said to be high pressure boiler. So you have got the point of definition about high pressure boiler. In a high pressure boiler, I am giving you some characteristics of high pressure boiler. The steam generation capacity generally varies from nearly 30 ton per hour to 700 ton per hour, with the drum pressure at about 160 kg per square centimeter, and the steam temperature at the turbine inlet is 540 degrees Celsius. My dear sons and daughters, I now give you an example of high pressure boiler and also a large boiler. For example, one of the largest boiler in United Kingdom. Why it is largest boiler, you will see the next. Under the control of Central Electricity Generation Board, produces 1,700 ton of steam per hour at a maximum pressure of 160 kg per square centimeter, and steam temperature there is 560 degrees Celsius at turbine inlet, and coal consumption of the unit, this power generating unit, is 220 ton per hour. In our country, in our state West Bengal, I refer to a standard power generating unit, that is Bakreshwar Thermal Power Station under West Bengal Power Development Corporation Limited. We used coal nearly 130 ton per hour per unit while producing 210 megawatt power at a rated pressure and temperature of the steam. You may ask me, what is the rated pressure and temperature? That means at a maximum pressure that can be allowed to rise in the steam of boiler drum, that is 155 kg per centimeter square, and the temperature of the steam being 540 degrees Celsius while entering the high pressure turbine. Here in the discussion of high pressure boilers, most important terms are number 1 circulation ratio, number 2 flame boiling, and number 3 departure from nuclear boiling. Let us discuss these terms one by one. Circulation ratio, the first term. The ratio of weight of water and steam mixture that is running in the circuit. This is to the weight of pure steam produced in the circulation. The total quantity of water and steam, its weight, and ratio of this weight to the weight of pure steam produced in this circulation of water from downcomer to the riser and again back to the drum. Here one term is also popular, that is top dryness, sometimes called top dryness fraction, which is the ratio of weight of pure steam in drum separated from mixture of water and steam to the weight of mixture of water and steam that came to the boiler drum for separation. Now, numerically I show the circulation ratio and top dryness fraction. Suppose the circulation ratio is said to be 3:1 or say 10:1. This means in the 3 kg water steam mixture or 10 kg of water steam mixture, weight of steam is 1 kg. Whereas top dryness fraction is 0.33 or 0.10, as would be the case of circulation ratio. The circulation ratio is the reciprocal of top dryness fraction. This means that is the top dryness fraction is equal to 0.33 means the quantity of steam produced from a quantity of water, that is 33.33% of total water has been transformed into steam, and 66.66% of water is yet to be transformed into the steam. That amount of water has not yet been transformed into the steam. Similarly, in the 10:1 circulation ratio, the top dryness fraction is 0.10. That means in a 10 kg of water, 10% of the water has been transformed into steam, and 90%, that is 9 kg of water, is yet to be transformed into the steam. So the dryness fraction is 0.1. Now we discuss flame boiling. If in riser tubes or sometimes in the drum, water bubbles at the metal wall stick to resist proper heat transfer from hot wall to cooling water medium inside, then this disturbance in smooth boiling of total water is called flame boiling. Another similar process of irregular disturbed heating is departure from nucleate boiling. Departure from nucleate boiling is coalescing of a series of water bubbles forming a thin barrier on the inner wall of hot metal. This formation of a layer of steam by coalescing of water bubbles with each other is called the formation of flame, and through this flame the disturbed passage of heat into the inner water and thereby the boiling of water disturbed by this flame is called the flame boiling. Vapor of water being bad conductor of heat resists easy heat transfer to the inner mass of water. That means in the core of the tube there is mass of water and the hot inner wall of the tube is unable to deliver heat to the innermost water content due to the formation of a film of steam, which is a bad conductor of heat. The flame boiling and departure from nucleate boiling interfere with heat transfer and lead to overheating of tubes. Rapid process of steam formation supports flame, and thereby the process of formation of flame leads to less efficient working of boiler. In the most of the high pressure boilers, there are several tubes or the riser tubes that carry water. You may question that why so many riser tubes are carrying water from bottom ring header to the boiler drum. Why these number of tubes are so many? If there is a single riser tube having bigger diameter to carry water to drum, then what would happen? The pressure loss would be more. That is, the pressure loss due to friction would be high. If you see, in place of several tubes of smaller diameter, I am using for a bigger mass of water to carry a bigger diameter of pipe, the single pipe. Now, what is the drawback of this pipe for which it is replaced by so many smaller diameter tubes? The huge loss of pressure show that friction is very high. We here mathematically prove the reason of use of number of riser tubes rather than a big pipe as riser. Let us assume the radius of single riser pipe, capital R. The height of the pipe to be, say, H, capital H. The density of the hot water in the riser pipe is rho. The acceleration due to gravity there is g. The coefficient of friction between water and the riser pipe wall is mu. Then we can write the friction in whole of the pipe, small f is equal to mu 2 pi r h into h rho g divided by 2. I can explain this, but this will take time. However, shortly, the force due to pressure of total water column in the pipe, that is equal to h rho g by 2. This is the average pressure. This we can assume this average pressure is acting everywhere. And the surface area is 2 pi rh. So the normal force on the wall of the riser pipe is 2 pi rh into h rho g divided by 2. And this normal pressure is related to the friction. That is, the maximum friction in this pipe is mu 2 pi rh into h rho g divided by 2. Obviously, this reduces to pi mu rh into h rho g. And this can be written by arranging such a way that constant terms comes out on the left side. Pi mu rho g h into h, that is h square, is the constant term, into r, the radius of the riser pipe. So we find that for a boiler the term pi mu rho g h square is nearly constant. You find the height of the tube or pipe is fixed. Generally it varies very little. Pi is a constant term. Mu, that is the frictional coefficient, if we take in this case, it is nearly fixed. Rho, that is also fixed, because temperature, if we take a constant for the final heating of the water in riser tube, then rho is nearly constant, G is also constant. So pi mu rho G H square is nearly constant. So we write F is equal to Kr, where K is the constant term. K is equal to pi mu rho G H square. Therefore F varies directly as the diameter of the riser pipe. Now if we want to reduce friction, then R should be reduced. How can we reduce R? R is the radius of riser pipe. This pipe handles water of mass m, that is pi R into H into rho. That is pi R into H. This is the total volume of the riser pipe. Volume into density. Suppose this is the hot water, the hot density is pi R square H rho. This is the total mass of the that is the total mass in the riser pipe. We find that m is equal to lambda R square, because pi H rho is constant. And we say where lambda is constant and lambda is equal to pi H rho. Pi is a constant, rho is nearly same for the particular position of boiler and the particular condition of the heat transfer, and H is also nearly constant. So lambda can be taken nearly as a constant. So root m is directly proportional to the diameter or the radius of the riser pipe, whereby the m is directly, or R is directly proportional to friction. If we now reduce the mass flow rate of water by say 9 times using the or distributing the mass through n numbers of tubes, that means I am distributing this m mass that was flowing through a single riser pipe, I distribute it among the n numbers of tubes. The friction would reduce by n, because m is directly proportional to friction, and also the radius of, as the radius of the riser pipe is proportional to friction and radius pipe is proportional to the quantity of mass flow in the pipe. So m, or under square root of m, is proportional to friction. And if m is reduced by n numbers of tubes, in each tube the m is flowing m by n amount of water, and hence the friction being reduced by n times, the pressure head loss would reduce by n times. It is clear? The friction is proportional to radius of the tube. Radius of the tube is proportional to the capability to contain water, and hence friction is proportional to the quantity of water flow. If this amount of water flow is distributed among n numbers of tubes, then the friction is reduced by n times. The other benefit is that heat transfer has increased for n number of tubes more than for single riser pipe. In a single riser pipe, the heat transfer to the water that is passing through the pipe is less than n number of tubes. The heat passing through the n number of tubes is more than heat passing through the single riser pipe. How this is possible? You see, the heat transfer rate is Q proportional to surface area, and so Q is equal to 2 alpha pi r into H. 2 pi r is the circumferential length of the tube and into height gives the curved surface of the tube, the pipe. I will not call it tube, this is a riser pipe. And it is proportional to the heat transfer. And alpha is a constant, where alpha is a constant and r is radius of riser pipe. If then n number of tubes has radius r each, then q dash, suppose the riser tube has got different radius, the riser tubes, each has got different radius and the height is same. So the number of tubes are also greater. So q dash is equal to 2 alpha n pi r h. Here the proportionality constant is the same because the condition is same. So q dash is equal to 2 alpha n pi r h. Now if nr is very bigger than r, capital R, that means the number of tubes is such that multiplied with the smaller radius nr is greater or equal to suppose r, then q dash is greater or equal to qr. If nr is very greater than r, then q dash is very greater than q. For improved method of heating in high pressure boilers, this improved method is the feature of high pressure boiler. The heating should be above critical pressure. In most of the high pressure boilers, some are subcritical, some are supercritical boilers. Now, during higher critical pressures, that is in supercritical boilers, the heat transfer is very good. The velocity of water in the tube should be increased to increase the heat transfer coefficient, and increasing gas velocity over the tubes to sonic velocity. What is sonic velocity? The velocity of sound at a certain temperature. It is important to mention the temperature for the propagation of sound through the air, and that is the sonic velocity. The heat transfer would increase if water velocity through the tubes are increased, and the gas velocity which transfers heat to the steam, the gas velocity over the tubes go to the level of sonic velocity, then the heat transfer is better. We now discuss the one-screw boiler. First of all, I tell you that one-screw boiler has no drum. So the weight of total tubes and furnace and such other accessories assembly has the value 20% less than that of the boiler with drum. That means the drum of a boiler nearly carries 20% of the weight of the total boiler. So without the drum, the boiler weighs 80% of the previous one which had the drum in its structure. Now I give you some information about the production of energy and the installation of higher magnitude of megawatt power plants. At the end of 7th 5-year plan period, that is in the year 1992, the national power production or generation was 42,344 megawatt. In the year 2005, the power generation was 1,18,600 megawatt in our country. This high level of generation was done by the installations of 500 megawatt, 660 megawatt and 800 megawatt plants. For the constructional and fuel price hike in recent years, that means the constructional price has increased and the fuel price has also hiked. and keeping installation price economic with higher fuel efficiency of the installed unit. The designers and also the production houses, that means the agencies who are going to install power plants, are interested to make 800 megawatt plants after 10th 5-year plan around the year 2007. After 2007, the year 2007, several high magnitude power generation installations have been made. The plants are having supercritical boilers, and boilers are devoid of any drum. So this is a once-through boiler. And the 660 megawatt power plants, obviously 800 megawatt power plants, are supercritical boilers, having supercritical boilers, and these boilers are not having any drum, that is the once-through boilers. The boiler can be of three kinds from the pressure level point of view. What are these pressure level point of view? The types of boiler from the steam pressure are divided into subcritical boiler, critical pressure boiler, and supercritical pressure boiler. Now I have to explain what is critical pressure boiler. We call it is critical boiler, but it is ought to say critical pressure boiler. The boiler having steam pressure of the value 220 kg per centimeter square, that is the critical pressure boiler. Now what is critical pressure? We now say that when water or any liquid boils to transform into vapor, at boiling point absorbs latent heat under normal atmospheric pressure, or say superincumbent pressure. The more the superincumbent pressure increases, boiling point increases. Of course, for those liquids, the boiling point increases which expand on boiling. Water, when becomes vapor, its volume increases, so its boiling point increases under pressure. If pressure increases, the boiling point increases. And thereby another event takes place. That is, latent heat value of the water goes on decreasing with the rise of pressure of the steam and with the rise in the boiling point. At a pressure 220 kg per centimeter square of steam, or the superincumbent pressure, the latent heat value of water just becomes zero. The moment that pressure is raised, the quantity of water immediately transforms to steam without taking any latent heat from the source of heat. Generally, the high pressure boilers are running below the critical pressure. This is the general installation capacities. They are subcritical pressure boilers, and so they have the drums because they are subcritical pressure boiler. In a TS diagram, this is the absolute temperature versus entropy diagram. That means the coordinates are temperature, that is the y coordinate, that is ordinate is the temperature, and abscissa is the entropy. You will find the curves each against a pressure value from very low to critical and supercritical level, showing the narrowing of latent heat line with the rise of pressure of steam. Suppose in the TS diagram, it is a coordinate diagram. It gives coordinates. And we draw the schematic structure of Rankine cycle. And in that cycle you will find, in that curves, there will be several curves. And there you will find the variation of temperature and entropy with the pressure of steam. Now, or the superincumbent pressure on the water that is boiling. And with the rise of pressure and temperature of the superincumbent steam pressure on the water, the narrowing of latent heat line, that means there is a line giving the constant temperature at the process of taking latent heat goes on decreasing. That means the line goes on narrowing. Narrowing means its value is decreasing towards the hem of the dome-shaped structure formed by the pressure lines and the temperature lines. At this point, that means at the critical pressure point, that means where the steam pressure is critical, there are lines of pressure of steam. The superincumbent pressures, the critical pressure, the line of latent heat becomes a point. That means this value becomes 0. The value of length of the line becomes 0 when its starting point and the finishing point are coincident. At this point, water transforms into vapor without any absorption of latent heat. Mind that, my dear sons and daughters. At this critical pressure, so it is called critical pressure. At critical pressure, the water or any liquid at their critical pressure transforms into its vapor without taking any latent heat. Here I tell you something about TS diagram, the processes, thermodynamic processes, point function, etc. in a very nutshell way. The temperature entropy diagram shows the schematic structure of Rankine cycle. It's a cycle. That means there are several processes starting from a state of, you see, water, and after going through several states, again come back to its original state, original point. So Rankine cycle, and at the modern times, this diagram shows modified Rankine cycle. The modified Rankine cycle is a little bit greater than the Rankine cycle in efficiency. I will show you this diagram in the next video. I will also show pressure volume diagram with explanation in the next video. I will explain TS diagram, the Rankine cycle in TS diagram and Rankine cycle in pressure volume diagram, and I will explain them. Now you see, the modified Rankine cycle, as I have told you, has more efficiency, cycle efficiency than ordinary Rankine cycle. I will explain everything in the next video. Please, my dear sons and daughters, wait a little bit for the upload of this video in a coming days. How would you find efficiency of a cycle? I will explain it later. Now I tell you what is a cycle. For a simple cycle to be completed, 2 processes are required in minimum. I gave you the example of a cycle, very common cycle, that is Carnot cycle. You see, the cycle in its simplest form is compression and adiabatic, completely by one isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression. There are 4 processes. And these four processes constitute a cycle. First position, the expansion has taken place with isothermal way. That means heat transfer is there. Heat has entered into the working fluid. Adiabatic expansion, that means there is no heat transfer or work transfer along the or across the boundary. The adiabatic expansion. Isothermal compression, that means the volume is compressed, is reduced. In a compression, volume is reduced. Here, the heat energy that was accepted in the isothermal expansion, the heat is now given to the surrounding from the boundary of the substance. And then adiabatic compression. There is no heat transfer or work transfer or any energy transfer across the boundary. Now what happens? From the first position, after going through some states, the substance comes back to its original state, the position. Here I tell you about point function. Now the point function is very important. So far, state in a thermodynamic system is defined. In a thermodynamic system, a state of working fluid is given by the values of particular values of pressure, volume, absolute temperature and its internal energy. There is also enthalpy, etc. You may mention them. If a fluid undergoes a thermodynamic cycle such that, suppose expanding to another state, it expands and its values of pressure, volume, temperature goes on changing and changed in the another state, and then returns to original state. After compression, it was expansion and it went to the other state. And from that state, it comes back to its original position by compression. Then it must get back. Mind that, my dear sons and daughters. When it comes back to its original position, it must get back exact original values of parameters, that is pressure, volume, temperature, etc. Its original value of parameters should be gained by it mandatorily. I say mandatory word, but you may say it must get back. The thermodynamic system may be shown by different diagrams. PV diagram, TS diagram, HS diagram, etc. HS diagram is enthalpy entropy diagram. I will explain everything. Now a state of fluid is shown as a point function or a point on such diagrams, and hence the function that relates the coordinates to show the specific place of that point on the diagram is called the point function. The point function denotes the position of a state of a thermodynamic system on the coordinate of diagrams. PV diagram, TS diagram, where the point is lying. And that point gives the exact differentials. More mathematically, we say the exact differentials like dV, that is differential volume, differential internal energy, differential temperature, etc., denote the point functions. That is, the cyclic integral of them is 0. That is, cyclic integral of dV, du, dt, all are equal to 0 as they indicate exact differentials. How this is possible? You may ask me this question. This is difficult to understand. The answer is a little bit lengthy. And my dear sons and daughters, I have run out the time and I have to finish here. But before that I finish, I will tell this in coming video, all these things. More thermodynamics will also be discussed then. My dear sons and daughters, if you boost me up by pressing the like button, subscription button and the share button, and leave comments in the comment box, give your suggestions. I will be enlivened to discuss all these difficult or easy things with you and share the knowledge with each other as I was doing for the last few weeks. So, my dear sons, hoping your bounteous favor, I finish here. My dear sons, I think you are all doing well. Have a good day and best of luck. Thank you.